Hello. Hi, everyone. Welcome to ICTS. It's great to see a full house and a lot of young people. I believe there's even a college from Kerala today, so special welcome to you for having, of course, come all the way to Bangalore, but then especially for this event, but also to all the people from various institutions in Bangalore. Some of you are here, I believe, for the first time for one of our events, so I hope you'll be back for many more. ICTS has a lot of outreach events. We have some here on campus, like the lecture you're here for today, but there are others regularly at the planetarium every month, the Copy with Curiosity. So I hope you will be coming for all these events if you're interested in physics, science, physics, mathematics, biology. We have a very wide canvas. So let me say a little bit about the lecture today. This is the second ICTS VISHVESHWARA Memorial Lecture. Professor C.V. VISHVESHWARA, maybe some of you have heard of him, but if not, I should say a few words. Professor VISHVESHWARA worked in the area of general relativity, or which is the Einstein's picture of the dynamics of gravity. So he worked especially on the properties of black holes and cosmology, the topic of today's lecture. He did his PhD with Charles Misner, a very famous gravitational general relativist at the University of Maryland, and one of the very important contributions that he made at the time was to understand why the simplest black hole solution is actually stable, why it doesn't just disintegrate. Why? And this is, of course, very important if you are going to find black holes, and this was much before. This was in the late 50s, early 60s, before people had even discovered these. So as a theorist, he studied the stability of the Schwarzschild black hole, the simplest solution of Einstein's theory that describes such a space-time. And the fact that it's stable, of course, means that you can hope to find it. You can find it in the universe, and indeed people have. But moreover, he he discovered what are called the quasi-normal modes of these black holes, which tell you that if you were to disturb this black hole by, let's say, something falling into it, or if two of these were to collide, and if you were to disturb it in some way, how would the resulting geometry relax to a final state? And there are very characteristic ringing frequencies, very characteristic modes that he found, which play a very important role in the detection of black holes through their gravitational radiation. And you might have heard about the epochal discovery by the LIGO collaboration 2 years ago, where they measured the gravitational wave signatures, the ripples in space-time. They measured it on Earth through an exquisitely sensitive detector, which matched with the signals corresponding to two massive black holes, about 30 times the mass of the sun each, colliding. The signal, you can see, has the imprints of these quasi-normal modes that Professor VISHVESHWARA predicted right in the more than 50 years ago. So in fact, Professor VISHVESHWARA came back to India. He was at the Raman Research Institute and the Indian Institute of Astrophysics, and he contributed a lot to the growth of the general relativity community in India, and with his pioneering research. But he also had another facet. He helped to establish the planetarium in the city. The Jawaharlal Nehru Planetarium was his brainchild, and I believe even from every part, including the design of the building and the whole environment, was something that bears his imprint. And for many years, he nurtured it. as the founder director. He started many programs at the planetarium, not just the regular planetarium programs, but other educational programs, the REAP program, which brings in science students. Perhaps some of you are going for such programs even now. It's been over 25 years since that program has started, and has actually produced many scientists, including one of our faculty, came through that program. So you can see the impact that Professor Vishveshwara had, not only in the cosmos, not only in our understanding of the cosmos and the big, but also in the city, in Bangalore, in Karnataka. So one of his last public appearances was at ICTS when we had an event announcing, at the time of the announcement of the LIGO gravitational wave discovery. So he was right here on the stage, and he was, in his very characteristic witty way, explaining the thinking when he made this discovery, but then he passed away in 2017, and last year we had the inaugural Vishveshwara lecture by Kip Thorne. So it was highly appropriate to start this lecture series with one of the people who was, of course, very instrumental in our understanding and detection of these gravitational waves. So we are very fortunate that today we are able to have the second Vishveshwara lecture in this series, and it's being given by none other than a very distinguished cosmologist, Professor Lyman Page, who is here for our cosmology program. I will not say more about Lyman Page. Professor Shubhabrata Majumdar will introduce him, but I just want to tell you that you're in for a treat from one of the people who really has helped us understand the birth of the universe. So I will now invite Professor Shubhabrata Majumdar from TIFR Mumbai to give an introduction to Professor Lyman Page.
Welcome, everyone. It's my absolute pleasure to welcome Professor Lyman Page, who is currently the James S. McDonnell Distinguished University Professor at the Princeton University, to give this second Vishveshwara lecture of ICTS TIFR. Professor Lyman Page, of course, is not unknown to us. It's not his first visit to India. He came around almost a decade back, 7-8 years back, to give the second Chandrasekhar lecture of ICTS TIFR. So it's double pleasure that he's back again to give the second lecture of the Vishveshwara series. Lyman received his BA in physics from Baldwin College in 1978. And then there was a period in which he was there in Antarctica, looking at cosmic rays, sailing the oceans, building his own boat. And then he went on back to do physics and finished his PhD from the MIT in 1989. And a year later, from 1990, he has been associated with the University of Princeton. Cosmic microwave background, the picture that you see at behind, have been at the forefront of precision cosmology for a very long time. And it won't be an exaggeration to say that Lyman has been in the forefront of cosmology with cosmic microwave background for almost 30 years now. He has measured the CMB from ground-based instruments, from balloons, and also from satellite observatories. He's one of the first and the original co-investigator of the WMAP satellite, which sort of established what is not known as the standard model of cosmology. Then he went on to become the founding director of the Atacama Cosmology Telescope, which is down in Chile at the high plains of Atacama Desert, and is currently a member of the executive board of the next generation of cosmology telescope from Atacama called the Simons Observatory. He is a fellow of the American Academy of Arts and Sciences and also a member of the National Academy of Sciences. Of course, he has won many awards, and I'm not here to list really any of them. I'll just say that he won the Gruber Prize in Cosmology twice, in 2012 as part of the WMAP team, and again in 2015, the Shaw Prize of Astronomy in 2010, and more recently, the Breakthrough Prize in 2018, which is last year. So it's all yours, Lyman. Please come on.
Professor Saraswati Vishveshwara is a biologist herself at the Indian Institute of Science.
Okay, so we get started. Okay, well, it's a great pleasure and a great honor to be back in India, and especially to be back to give the VISHVESHWARA lecture. Thank you all for coming. What I want to explain, give you the context, is this background map right here. So I want you to keep that picture in your mind as we talk, and I'll introduce a few aspects of it right now, and then we'll keep coming back to it. So first off, what's the scale? So that is the whole sky unwrapped. It's like looking down at a two-dimensional picture of a globe, like you see just a map of the world. Sometimes they have that oval shape. That's what that is, except looking up. And what is it? It's a heat map of the early universe. And except it's a heat map. Not, you can sometimes see heat maps from infrared pictures of houses and things like that, but the heat levels are tiny. And from the bluest blue here to the reddest red are a few hundred millionths of a degree. Okay, so these are very tiny differences in heat across the sky. And this is called the cosmic microwave background radiation. So I'll keep using that term. I'll call it the CMB. I'll slip into that jargon. I'll try to avoid it. But if I say CMB, it is this map that we're looking at. And just to prime you, this is a map of, we can think of it as a map, a direct result of quantum mechanical fluctuations in the birth of the universe. And yet we see it now today writ large across the sky. And what I want to do is fill in that picture, and I want to do it focusing on observations. So hopefully everything I say, the idea is everything I say is directly tied to an observation. Okay, so it's won't be too much speculation here. Okay, I want to start just by giving an overview of cosmology and how to think about it, and going back and try to think about what that picture we see of the sky is. So first, how big is the universe? And I want to start with this because it's one of the most difficult things to get a handle on, are the distances involved. They're absolutely incredible. Okay, so you think the moon, right? It's pretty common. I'll use the moon as a standard in a number of cases. So the moon is about 380,000 kilometers away, right? So not too far, right? A good car, you could drive to the moon, right? So it's a really sort of a human distance. And the moon it's 1 light second away, roughly. Okay, that means it takes light traveling, well, we always say 186,000 miles per second, but you guys don't do that. Okay, so it takes light roughly a second to get to the moon. Okay, so the moon's pretty nearby. The sun, our next most friendly nearby object you know about, it's 8 light minutes away. Okay, that means if the sun were to disappear, we would not know it for 8 minutes. Okay, it takes light 8 minutes to get from the sun to us. Going up at the next largest scale is the galaxy. So on a clear night away from the city, if you look up, right, you can see the Milky Way. Right? That's our galaxy. You look up and that's a vast array of stars and dust. And here's a picture of it from the COBE satellite. And so this is our galaxy, the Milky Way. And in the middle of that, the middle of the Milky Way is about 25,000 light years away. right? So if there were some extraterrestrial you wanted to talk with who was in the center of the Milky Way, right, it would be a really, really slow conversation, right? You know, it's high, and presumably they get it. 50,000 years, you know, how are you, right? So it's slow. So we'll keep building up the scales in a minute, but a number we'll keep coming back to is the number of stars in the Milky Way. It's about, in rough numbers, it's about 100 billion, okay? And I'll tell you that. Okay, so there are about 100 billion, and that number is just 1 followed by 11 zeros. Okay, it's a big number. So it's a really big number. So to get it in perspective, you can think of like Jeff Bezos or Bill Gates is worth about $100 billion, okay? So they have $1 for every star in the galaxy, okay? Or a more biological version is there are about 100 billion neurons in your brain, okay? And if you have a sweet tooth, if you had 15 meters by 15 meters by 15 meter box, and you filled it with M&Ms, there'd be about 100 billion M&Ms in there to give you the scale to try to visualize it. Okay, so we'll keep coming back to that 10 to the 11, that 100 billion number. Okay, so this is now again another a picture and a movie, and this is made of. Hopefully it started. Not quite. There we go. So these are all galaxies. There are no stars here. Okay? They're all galaxies. This is from the Sloan Digital Sky Survey. These are all galaxies, and each one of these has about 100 billion stars in it. Okay? And this goes out to about 1.3 billion light years away is the extent of this. And I want to show you this for 2 reasons. One is you can see we're taking a step out from the Milky Way, right? These are all Milky Ways of various types. We're taking a step out from the Milky Way to these huge distances. But the other thing I want you to keep in mind is right, this is a way different picture than that first one I showed you of the heat map of the sky, the cosmic microwave background. Right? These galaxies are clumped. They're made of various types of matter, and they're all clumped up. Right? So this is what we see around us. This absolutely stunning movie put together by this team. And this is now from the Hubble Space Telescope. So here, this is the Hubble focused on this what was called the Hubble Ultra Deep Field. Near the Fornax constellation, and so here's just this little this picture of where the Hubble is, looking out deep into space, and these, except that they have X's around them, these are all galaxies, and the first thing is to notice is they're just how big of an area is this? There are about 50 of these could fit inside the full moon. So 50 of these images could fit inside the full moon. So if you look up at the sky, the sky's just plastered with these. And you can go and you can count them. And of course, there's not quite the resolution here, so you get fancy computer algorithms and you can count them. And in this image, there are about 10,000 galaxies. So you can do the multiplication, and you can say, well, if there are 10,000 galaxies in that image, and there are 50 of those per full moons, and there are and full moons across the sky, how many galaxies are there in the sky at this depth? And there again, they're about 100 billion in rough numbers. And the amazing thing about the Hubble Ultra Deep Field is it looks out so far, it sees all the galaxies along that line. So if it were more sensitive, it might see a few more galaxies, but it wouldn't see a whole bunch more. So you can think of this as the observable universe containing just 100 billion galaxies. Okay, so 100 billion stars per galaxy. the observable universe contains 100 billion galaxies. And that's something that's, well, we'll go through a few slides so you can get your head around that. But that's this idea of the observable universe we'll keep coming back to it because it's key to thinking about that first image I showed. And with this picture, this Hubble picture, and with the Sloan Digital Sky Survey, those galaxies, they're all rushing away. Okay, for the Sloan, not quite. The nearby ones aren't quite rushing away, but the further ones, they're all rushing away from us. And this was first found. What was recently is called the Hubble-Lemaitre relation, and they found this back in the early part of the 1900s, and they're rushing away in a very special pattern. That is, the further away it is, the faster it's moving away. And more specifically, if it's twice as far away, it's moving twice as fast. 3 times as far, 3 times as fast. And you might at first think, you know, okay, everyone's trying to get away from us, right? That's for who knows what reason. But that, you know, or that we're some special, that we're in the center of the universe. But that's not the way to think about it. And we're special, but we're not that special. And imagine, just first off, just imagine that this pattern goes on forever, for right now. If we went, all of a sudden we could put ourselves on that guy, right? It'd be like jumping onto a car and another car, well, it'd be like all of a sudden, if we were zooming past that, let me say it differently. If we could just put ourselves in that guy's position, right, and look back at us, we would see us going off to the left there at the same velocity. We'd be at rest now with respect to our neighbor. Right? So no matter where you are in this line, you get the same picture with exactly the same pattern, twice as far away, twice as fast. So what's a good way to think about that? And it's not, you might immediately think we should think of these galaxies in this picture as just a big explosion. I mean, sort of the Big Bang brings that to mind, as an explosion of all these galaxies into space. But that's not a good way to think about it. A much, I think, clearer way to think about it, and this is, again, it's a way of thinking about it, is you can think about not these galaxies moving throughout space, but space being made between the galaxies at a constant rate. So another way to sort of visualize that, right? If you had a rubber band, say a long rubber band like this, and every 5 centimeters you glued a pebble onto it, right? And now, so there's your rubber band, and now you stretch the rubber band, right? The pebbles, you wouldn't say the pebbles were exploding, right? They all stretch out, and the amount of rubber band between each pebble just increases. Right? So we can think about the expansion of the universe that way, as a sort of as a making of the space. And so you see, it's again, so we have this picture, and as long as this line can go on forever, it doesn't matter where you are, you get the same picture. Okay, so good, and it appears the same from all vantages. Okay, so now let's forget about the expansion for a minute. We're going to put that aside. And I want to make the very provocative statement, so this is so we can connect these two pictures, that the universe is infinite. And when I say that, I mean by as far as we can tell by measurement, it is infinite in extent. There's no measurement that we currently can make that we can tell the difference between an infinite universe and a non-infinite one. So we're just going to say it's infinite. It goes on forever. Okay? But if you go and you think of this last picture here, right? Oopsie daisy. You think of this last picture, if all these galaxies are going apart right now, we can reverse that, right? If they're all moving apart right now, they're all closer together in the past. And we can keep moving that back, and we can say they all must have been on top of each other. and we can do that very carefully, we'll get to that a little later, we can say they were on top of each other about 14 billion years ago, roughly. So what is the universe like around us now? It's very much like that Sloan Digital, it is especially around us, like that Sloan Digital Sky Survey. So that's sort of in the, like this background here. So right at this instant, it's like that. But we know, to a reasonable approximation, because the universe has a finite age, that 14 billion years, right, that we get from extrapolating all those back, and because the speed of light is fixed, we can only see so much of it. Okay, we call that the Hubble patch. So we can only see so much of it, and we call this edge here the edge of the observable universe. And so what you can imagine will happen is the microwave background is going to come from us from right there. That first image is going to come to us from that sphere. Okay, so that's the diameter set by roughly by 2 times the speed of light times the age of the universe. Oops. Okay, but now, because the speed of light is finite, right? Telescopes are, right, it takes 8 minutes to get from the, from light takes 8 minutes to get from the sun to us, and 25,000 years to get from the center of the galaxy. Because the speed of light is finite, telescopes are like time machines. That means, still ignoring the expansion, when we look out deeper and deeper in space, we see things as they were younger and younger and younger and younger, because the light has taken, we see the sun as it was 8 minutes ago, and the center of the galaxy as it was 25,000 years ago, and we look out far enough, we see the universe as it was 14 billion years ago. So that's that, and so that's getting at this first picture, and you can see that, again, we just see distant objects as they were when they were younger, so that's what we see by looking out. And here's a Hubble Space Telescope looking out, and you can see it sees out to where it can see all the way out to here past where just out to where galaxies start to form, and that's why we can say we can count the number of galaxies in the observable universe. It doesn't mean in the whole big picture there aren't more, they're an infinite number, but we only have access to this Hubble patch, only to that 100 billion. Okay, and now I want to add the expansion. And what happens with the expansion is that light from the edge here, light from the edge of the observable universe, was emitted when the universe was much more compact, and the expansion has just stretched all the wavelengths of light. Okay, so what it's done is it's turned visible light into longer wavelength versions. Okay, so that's what the expansion has done. Okay, so I now want to start to pull this all together with a number of things I've said, and there's a whole bunch in this picture, and let me just walk through some of it. So here's the idea. This was the WMAP satellite is there, and this picture of looking back and back in time is like looking this way. Okay, we're just looking back. We see galaxies around us now. They were younger and younger and younger, and we look back, and now here's where they were forming, and there's a gap there. And we look back here to the cosmic microwave background. Okay, that's that first image I showed you, that picture, and you'll see more of them. We look back to the cosmic microwave background, and then we don't, in light, we can't really look back further. Okay? So let me run the picture the other way, so you can see what's going on. And so the idea is there were some type of fluctuations in the early universe, some quantum fluctuations, and this process called inflation, which I won't talk about other than to say it was this absolutely enormously rapid expansion of space, enormous, and it's like 1 followed by 30 zeros. Expansion of space. That's like taking the size of a proton and expanding it to it was the size of 100 times the solar system. Just this absolutely enormous expansion of space. And so this expansion took these quantum fluctuations and made them large, writ them large across the sky. And then the universe went into a more casual rate of expansion, and all the stuff in the universe responded to it. So this cosmic microwave background that we see was doing that right then. And so let's just see what happened during that time. And so I just want to focus in right here. And this is what we call the era, there's an era of decoupling. So the universe, as far as we're going to worry about, was just protons and electrons and photons bouncing around. And it just had this fiery beginning, and it expands and cools and expands and cools and expands and cools. And all of a sudden, when it's roughly about half the temperature of the sun, instead of all the constituents scattering off each other, hydrogen can form. And it's sort of like, you can think of it when you're outside in the fog, and you can't see very far, and nothing's very clear around you, and all of a sudden, it gets hot enough for the fog to burn off, boom, you can see everything, right? So, in somewhat similar way, all the electrons glommed onto the protons to make hydrogen, the light stopped scattering, and that light was free to roam the universe. And that light is the cosmic microwave background. And this is called the epoch of decoupling because it occurred, well, epoch of decoupling because the light decoupled from the matter. And what that allows us to do, going back, is to then look back, the light decoupled, and that light has barely interacted with anything since about 400,000 years after the Big Bang and us. So it streams by all these objects here to a good, reasonable approximation, and we observe it. So that's how we can look back here, and we can see what's going on at the edge of the universe. And the picture that we have and will continue to develop over the next few minutes is that these quantum fluctuations here were manifest as these tiny fluctuations that were blown up. We can think of them now as fluctuations in the strength of gravity. And while this process was happening, all that plasma, that early universe, was responding to those fluctuations and started to flow into them and compress and rarefy and compress and rarefy. And those compressions and rarefactions are what lead to these tiny temperature variations here. And then those same potential wells, that same gravitational landscape, seeded the formation of all the rest of the cosmic structure in the universe, right? So everything we see around us, all the structure that we see, that Sloan Digital Sky Survey, the clumpiness of that comes from these quantum fluctuations, and we get this picture of them from the early universe. So that's the idea. And let me show you one last, I think, just a wonderful video, again from the Sloan Digital Sky Survey team, and Mark Subarow's one of the champions here. So these again are just galaxies, and these are the positions of real galaxies, and a little artist rendition on the artist license on the coloring. But these are early days of the Sloan survey, so the sky wasn't as filled in as it is today. So these are actual positions of galaxies. And as we zoom out, we're looking back and back, further and further. That's just to guide you, of course. We go back further. We look further away. We see those are younger galaxies. We see when the universe was about roughly half its current, twice as compact as it is today. They're called the luminous red galaxies. And then we look out and see these objects called quasars. And then as we keep looking out, see in a minute, we keep zooming out, we go all the way back to the cosmic microwave background. And so we observe all this, and now much more of the sky than that. And of course, we observe this cosmic microwave background. That's now shown spherically what was shown flat out on that first slide. And so the picture then to keep in mind is that these hot and cold spots here, right, indicate the seeds that eventually led to the formation, the seeds, the variations in gravity that led to the formation of all those other galaxies around us. And it's a pretty mind-blowing picture, right? But it hangs together fantastically well with the data, as I'll show you. Oops. It's worth seeing again, but I know you don't want to. Here we go. Okay. So is that good? Okay. So that's the framework in which we want to think about the cosmic microwave background and about cosmology and about galaxy, and about sort of all this beautiful cosmic structure we see around us. So how do we measure it? You know, what is that first picture? And this is what I've spent most of my life doing. And here's the idea. The idea, it's really simple. And so the CMB, cosmic microwave background, remember when it decoupled, it was about half the temperature of the sun. So the sun is about 6,000 degrees, and so it's about 3,000 degrees at that time. And a few things. One, is how hard is this physics? I mean, it's 3,000 degrees. It's not that hard. You know, this is very well-known physics, so it's not a lot of extrapolation here. So that was 3,000 degrees. The universe at that time was about 1,000 times more compact. And the expansion of the universe just cools it. So that 3,000 degrees becomes now 3 degrees. And it's now 3 degrees above absolute zero. And so that radiation, which was once hot, is now cold, really cold. But if something's 3,000 degrees, right, it's about 1,000 times cooler than the sun. And that means instead of shining in visible wavelengths, it shines in the microwave. Okay? So the microwave is just the upper end of the microwave background, of the microwave band, is just about at the really high channels of your TV. So, and this is a slightly, I know everyone, you know, you have all MPEGs and things like that now, right? And no one hooks up an antenna to get a broadcast, but your parents did, okay? So if you have an antenna, if you just put an antenna up to the sky, and you hook it up to a TV, and in the US, if you put it on channel 69 and looked at this, you'd look at the fuzz, and you have to make sure there are no other stations broadcasting there. You just look at the fuzz, and 1% of that fuzz comes from this radiation. Okay? It's pretty amazing. 1% of that fuzz comes from this radiation. And remember, what we're looking at, what we care about, are tiny temperature variations, right? That first map wasn't the absolute temperature. It wasn't 2.725, but hundreds of millions of degrees variations in that temperature. And so what you do is you just hook up this antenna, and you just point it at different spots in the sky. And you say the fuzz is 1% here. Okay, it's 1.001% here. It's 0.9995% here. That's the measurement in a nutshell. That's what we do. We have to be a little more careful. And here is a picture of how it's been done from space. So this was the satellite I was involved in, and this is its more recent and more powerful cousin. This is the Planck satellite. This is WMAP, and these are the measurements from these satellites are the foundation of the standard model. But you can see for WMAP, that light would come in here. It came in both sides because we wanted to make a differential measurement. Light would come in here, bounce off, whoopsie daisy, bounce off there, and bounce into the receivers in there. And we measure them from both sides, right? But you can look at that. It's just like a TV satellite dish, right? It's fancier, but that's all it is. And we had two of them because we didn't care about the absolute temperature. We just wanted to measure the difference. Okay, so we took measured the difference in the sky in two positions. Okay, and now this is a large field. Lots of people are doing it. Here are colleagues at the South Pole with a South Pole telescope. I'll show you some results very briefly from these. The Atacama Cosmology Telescope in Chile, and there's another polar bear telescope. And so there's lots of these measurements going on. So what is it that we actually measure? So this was with the WMAP satellite, and this is one particular frequency band. This is about, the wavelength is about 0.5 centimeter. And this is really, that first picture that was shown was a bit sanitized. So this is really what we measure. And what you see here, these are these same fluctuations I talked about, right? A few hundred millionths of a degree from hot to cold. And this is the emission from our galaxy. So this is the Milky Way, right? So you have to imagine, if we want to study these hot and cold spots, we have to get rid of that. And so we just cut it out of the maps, more or less, when we do the analysis. So you can forget about that bright stripe. But now let's zoom in. So here's a little spot below it. And let's zoom in a little more. Okay, so this is now, you can see as a zoom in, this is roughly 5 degrees on the sky, right? About 10 full moons across. And that's what the sky looks like. And this is not due to the resolution of the instrument, right? The resolution of the instrument is much finer than this. These are the fluctuations in the cosmic microwave background. This is what we're after. That's what you see here. The noise is much smaller. But you can look at that, and you can see that there's a characteristic scale here, right? These spots, they're random, they're different sizes and all that, but they aren't all this big, and they aren't all sort of pixel sizes, right? There's somewhere in between. There's a characteristic size for those spots. And that's going to be the key. So let's look at how this works. So here is, so here then is a zoomed in map of the sky. The last one was 4 degrees by 5 degree. We saw the 5 degree scale. So this is zoomed in a little more. So this is just a section of sky, 4 degrees by 4 degrees. And you can see now the color scale, little larger than it was before. And this particular one is centered on the north celestial pole. And I know for us that's easy to see, and for you guys it's only 13 degrees above the horizon, so it's a little bit more difficult. And for scale, right, the moon doesn't get there. For scale, there's the full moon. But just so you can look up, just to help you visualize, right? The next time you look up at the night sky, when you see the full moon as it is just about now, think of the sky being full of hot and cold spots like that. They're out there. That's what they're like. Where you look, they are there. Okay? It's just, you can't quite see them because it's in the microwaves. Okay? Now, you can take all these hot spots, and you can come up with your favorite algorithm. There are people in the audience here who've come up with especially fancy ones. But you can take your own algorithm, just say you stack it, you pick that point, you pick that point, you pick that point, you pick that point, and you just stack them all together over the whole sky. So this is from the Planck satellite, and this blue is 0, and this is just a stack. You just stack all the hot spots. And you can see it has this characteristic scale. Just like you could see going back here, right? There's sort of this characteristic scale blob size of about 1 degree. Here's this characteristic scale. That's all the spots. I mean, this is real data. That's all the stacked spots. So what does that come from? What does that characteristic scale come from? And how do you get the hot and cold spots? And here's then the picture. So we've talked about elements of this, right? Those blue dots are that primordial plasma, right? From back when the universe was just going through this process of hydrogen forming, and there are free protons and free electrons. And this is the idea of this gravitational landscape. So that's just, those are mountains and hills. You can think of a gravitational landscape like that. And that was laid down by some process like inflation. And now the plasma flows into it. Here's this little, it's in a loop here, this picture from Wayne Hu. The plasma flows into these gravitational potential wells, this gravitational landscape. It flows in, and it heats up. And there's a characteristic size here, the spot size. It's just the speed of the plasma, those dots, times the age of the universe at decoupling, right? All of a sudden the universe decoupled and there was that plasma was no longer there. It was all, you know, it's in hydrogen atoms. And that sets a characteristic scale. And that is about a degree. And here's the beautiful thing, is the physics is so known that you can compute that to high accuracy. So this now becomes, since we can compute that scale, it becomes a standard yardstick. And now we can it's a standard, we can think of it as a fundamental mode or a footprint or it's a characteristic scale in the universe, a spot. And now we look over, we can do the same thing with cold spots as hot spots. And now we can measure the average angular scale of that fixed thing. Think of it as a fixed, we know that fixed distance in physical units. And we can measure it to incredible accuracy. Okay? So we can measure, it's just now we have a simple triangle, right? We have an angle, we have a size, and from that, we can just make hay, right? We can get from, since we have an angle and a size, we can get the distance. From the distance and the speed of light, we can deduce that the age of the universe is this, right? So this is the latest from the Planck satellite. So this is, we can get that the age of the universe to percent level accuracy from measuring these hot and cold spots on the sky, right? It's pretty, so that's the age of the universe. And there's much more information in there. So here is now, let me just explain this. This was, I feel I didn't want to show something that was too technical, but this was in our local paper, so I thought it was okay to show you. So on the y-axis here is, you can just think of this as amount of fluctuations, okay? And on the x-axis is angular size. And so this big peak here is, right here, that big peak is right around a degree, and that's from the plasma flowing into those wells, okay, and making all these hot and cold spots, right? So that's at a degree, and that we call the fundamental mode. But the plasma does more than that. It sloshes around, it flows in, it flows out, does all that sort of thing. So this is rarefaction and compression, and there are a whole series of peaks that have been measured. And now, but here's the thing to take away. The data here, and there are a couple of different versions of it, the data are those black and red dots with error bars. Okay, so there's tons of information in that map. And this model here is the model of the universe that describes in the global properties of the universe. And what you should take away is the data are incredibly constraining. Right? If you have a model of the universe that can't match these data, it's not a contender. Right? So we really are narrowing in on the right model for the universe that explains it. And let me show you some pieces of it. So here's some parameters of the model. Here just three, and this is the this is the Microsoft pie chart version that we show. But it's the basic model, and it has only 6 parameters. That means we can describe the large-scale properties of the universe with only 6 parameters, which is pretty amazing. Right? It's just this, I mean, it's a mind-blowing state of affairs. And so here are 3 of them. And so we see that of the total effective mass energy density of the universe, 5% are atoms, right? Only 5% of the universe, like all those pictures I showed you of galaxies, all that was only 5% of what's out there. Another 25% is some new form of matter. And we don't know what it is. We've heard lots of talks about it today. There are searches all over the world for what it could possibly be. We don't even know what form it is. We don't even know if it's one kind of matter, right? We don't know what it is, but we know it's matter. We know it's matter because because we know we have to have a matter term in that model. And so, and then this other 70% is this other, even more weird term called dark energy. Let me get to those in 1 minute. And there's a great, I heard today in one of the lectures, there is a term, not the universe, the unknowniverse, right? Because we only know about 5% of it. The rest, so it's an incredibly well-fitting model, but we don't know 95% of the universe. We just don't know what it is. So so the model's fantastic, right? You can see how good a fit it is, right? If you don't tune those things that way, you don't get a good fit. But what is this? But the dark energies especially, right? It has no foundation in any fundamental theory of nature. And it is though the vacuum has an energy density with it, right? It's like we don't fundamentally know what space is, and this energy density drives the universe apart. And most think that this dark energy represents a missing piece of the theory, especially if you're an experimentalist, right? It's usually the theory that's not quite right. So, but we just don't know what it is. So, you know, maybe one of you guys will figure it out. And again, we don't know what the dark matter is. So here's the abbreviated standard model of cosmology that we have. So at some very early time, a quantum field impressed on the universe this gravitational landscape. And we measure the characteristics of that field. So this picture of the microwave background is a picture of the quantum field from the birth of the universe. And if you could look up with microwave eyes, that's what you would see. And the matter fell into these valleys to form the structure of the universe. The matter that came out of the Big Bang. It fell into this quantum into this gravitational landscape to form all the structure. But only 1/6 of the total amount of matter is familiar to us. We don't know what the other stuff is. And now the universe, the future of the universe, is driven not so much by the matter. It's going to be driven by this dark energy, this vacuum energy. And it's started to accelerate, and it will continue, those galaxies will continue they'll accelerate apart instead of just moving apart at some constant velocity. So that's the picture. I want to, let me spend the last few minutes here talking about frontiers and where things are going. And this is for a few reasons. One, it's still an incredibly exciting field. There's tons to be done. And just to talk about links between gravitational waves and black holes and what's going on in cosmology. And the big question is, are there gravitational waves from the birth of the universe? So what is a gravitational wave? And we heard a bunch about them in the introduction, but what is the picture? It is, if a gravitational wave is propagating that way, it is space is stretched this way, expanded this way, compressed this way, expanded this way. It goes like that. That's a gravitational wave. That's what these are supposed to denote. Okay, so what is a strain? So what does it mean? So it's measured in strain. So what a strain is, this is roughly a meter stick. What a strain is when that wave goes by, it compresses this stick. Okay? And if this were a meter and it compressed it by 1 centimeter, that would be a strain of 1%, 0.01. Okay, so that's a strain. And so a gravitational wave would squeeze it here, and then as it went by, it would squeeze it, expand it, and squeeze it, expand it. And if the strain was 1% or 0.01, it would be squeezing this and expanding this by a millimeter. So LIGO, as we heard, discovered 2 inspiraling black holes that emitted gravitational waves as these black holes coalesced. And the strain was that, not 1%. That is 10 to the, there should be about 20 zeros in there. The strain is about 10 to the minus 21. Tiny minute. The strain was about the difference in 1 human hair between Earth and Alpha Centauri, the nearest star. Okay? This is an incredible experiment, incredibly sensitive. And this wave oscillated, that was measured from these 2 inspiraling black holes, was oscillated at about 100 cycles per second. okay, 100 hertz. So one of the coolest things that's, I think, my cosmology hat on, that's going to be happening in India soon is India LIGO. And if you can, you should get involved with it. This is LIGO from, this is one of the LIGO detectors from Washington State, and soon there'll be a version in India. And what's fabulous is it's fabulous for a couple of reasons. One, it will be a key piece in localizing these sources on the sky, a key piece in this network of gravitational wave observatories that is being developed. But the other thing, and again with my experimentalist hat on, is the experiments and the techniques are they're deep, and they're intellectually challenging, and the field has just started. There's a ton of things to do to improve these detectors. They're nowhere near their fundamental limits of measurement, right? There's lots and lots of things that can be done. So it's just it's a playground for future experimental physicists. So it's just an absolutely fantastic project. Okay, so that's LIGO type. Those are black hole type, as our lecturers worked on for all these years, right? So what are we doing with the universe? So we're searching for gravitational waves produced by the extraordinary densities in the beginning of the universe. And the picture is there. You remember that from that sphere you saw? We think of the microwave background as a sphere around us. It is like gravity has stressed that. It's squeezed the universe. The whole universe. It's just squeezed it a little bit. Okay? But the strains are enormous. Right? These are strains of a part in there 10 to the 5, roughly. Okay, so much larger strains. And the strains that we're after, looking at the microwave background, correspond to the width of a hair compared to the height of a person. Much larger. And instead of 100 cycles per second, they're 100 cycles over the age of the universe. Okay, so they're fixed as far as we can tell. And if we can find them, these would be an incredible new connection between gravitation and these quantum processes in the early universe that gave rise to all this structure. And of course, a new test of the cosmological model. So how do we do it? This is a picture. So this is the only simulation I'll show you. So this is a picture. This is 18 degrees on the sky, so 36 full moons. And that's the regular old temperature fluctuations that you've been seeing in the background. And these little arrows here are the polarization. So not only is this radiation vary in intensity, but it's polarized. If you could put on microwave polarized glasses and look up at the sky, you'd see it one way, and you'd turn it, and it would look different. Right? Just like, if you're driving along in a car and you have Polaroid glasses on and you look at the hood and you turn them, it looks different, right? You reduce the glare depending on the angle of the polarizer. Same thing here, but the polarization signal is tiny. The ones we're after correspond to about 100 billionths of a degree centigrade, so absolutely tiny signal. And I'll put this in perspective. So this is now, this is a current plot with all the data that was shown actually through, not all the data in the last few years as of last August. And this is from the Planck satellite, from the ACT experiment, from the South Pole Telescope experiment, from the BICEP experiment, and from the polar bear experiment. So those pictures I showed you earlier. So, and that plot I showed you earlier with the rarefaction and compression, that's that top one. You can see it's just measured super accurately, right? This is, and there's a model that goes through there. That same model predicts the polarization. There are the data. This is why you should believe that have the right model, even though We don't understand 95% of it. We know the characteristics of those other pieces. And this is then another version of it. And this signal we're after hides way down here. This is where the signal from gravitational waves, from the birth of the universe resides. It's way down here. So this is the signal we're after. This is the bicep Keck experiment in the lead right now of measuring it. But there are a bunch of groups going after this. And one in particular, I want to show you, this is the new effort, you can see it's international. This is from the Simons Observatory. Brian Keating's the director, Mark Devlin, Adrian Lee, and Suzanne Staggs are the spokespeople for it. And you can get the sort of an idea of what's going on. This is a picture of where it is. But it will, this is if you visit Chile, and you go up to 5,200 meters, there's just a whole suite of telescopes there. And this is one, this is the ACT telescope. You'll see other ones in a minute. And the idea is to add, there'll be 5 new telescopes there in the next 5 years, all working on making the microwave background. This is the CLASS experiment from Johns Hopkins. This is the polar bear Simons Array. There'll be about 10 total telescopes up there, all measuring the microwave background, and about half of them are going to be looking for this signature of primordial gravitational waves. And so it's going to happen, and maybe in sort of 5 to 10 year scales, we'll know if they exist at a measurable level. So let me stop there and thank you. Any questions? Okay.
Journey. Would you take questions?
Oh, of course, yeah.
So we can take questions. Please put up your hand. Wait for a volunteer to bring a mic to you, and please keep your questions short, relevant to the topic.
Hello. Hi. Just wanted to know, the wave is characterized by its frequency. So you told that it's 100 hertz, what was detected by gravitational LIGO. What is the information you can extract from that frequency parameter? Like why it is 100 hertz?
Oh, for LIGO? Okay, so for LIGO, this is, I mean, that frequency was set by, those really come from 2 sources, right? Spiraling into each other. And that they just get going so fast in the end that these 2 30 solar mass black holes, they're actually spiraling into each other at around 100 hertz. And that's why that signal is there. That's why it's at 100 hertz. For the universe, it's the same sort of physics. It's still gravitational waves from Einstein's general theory of relativity. But the waves aren't anywhere near that, right? It's 100. They oscillate roughly 100 times over the age of the universe, you can think. It's so slow we can't see that. It's like they're frozen in. And what we do is we look, there's a characteristic signature in the polarization that we're trying to see. And that's what we're after.
But for detecting such low frequency, you need to have sensors which are like way apart, right?
The universe. So we look, it's the universe. So we look with our telescopes, absolutely. So we have our telescopes, we see it in the cosmic microwave background. So that way apart is the universe. Exactly.
But maybe you're asking direct gravitational wave detection on those scales.
Yeah, no, it's
that's not.
It's the only way to do it is through this. Yeah.
Professor, what is the rationale behind the CMBR uniform anisotropic temperature to settle at E Kelvin approximately the Napier's constant? And the second, a small popular science novice question: is it possible to simulate the CMBR using my microwave oven if I'm not hungry?
Okay, can you? I missed.
I think the first part you were asking about the significance of the special number, which was
it was close to E. It was close to E.
Oh, very close to E, yeah. What a coincidence, right? That's a good way to remember it. It's 2.72, it's not E, it's 2.7255, depending on who you talk to, maybe 5.6, so it's not quite E. But yeah, no, everyone's noticed that. And so I'm sorry, the second was?
The second I didn't get as well.
The CMBR using my microwave oven if I'm not hungry.
Oh, is it possible to simulate it using a microwave? Sure, but it's faint. I mean, when we build these detectors, we just use microwave sources, if that's what you mean, just to test their characteristics. But if you're asking if there's a way that something else in nature could fake us out on the sky, and the answer there is no. And it's a very definitive no for the following reason. And that is that the cosmic microwave background, it's called black body radiation. This is, Planck discovered the equation. And it's got a very, very specific function for the intensity versus the wavelength. And to the limits of measurement, the microwave background follows that. And that state, and that function means that that radiation had to be in thermal equilibrium with something at some part in the universe. And you can't fake that. So it's there, it's on the sky, it's from the early universe.
So according to you, the whole model is actually based on Big Bang theory, right? Like the whole universe is expanding and it's like moving away from itself. So assuming that all of this happens due to the heat energy or the temperature which was there during the initial boom, the energy was used to move away. So as the temperature has reduced, it's almost 2 degrees according to what you said, 2 or 3, I guess. So assuming it, as soon as it goes off to 0, all the particles will stop moving away from each other and they'll start coming back. Okay, is it possible?
No. So here's what's happening is, first, what you say is not impossible. It's just not our universe. What's happened in our universe is that, so there was this, the expansion was large, and if there had just been matter, right, because it's gravitational, it would have been decelerating. There were just matter. But now there's this dark energy, and this was discovered in the mid-1990s. And this dark energy is causing the acceleration of the universe. And so it will absolutely get colder and colder and colder and colder, so but it's not going to come back.
As soon as it becomes cold, it will become like almost equal to absolute 0.
Right.
And then there will be no energy for it to expand. So it will start contracting, and then due to the gravity, it will start.
That's the amazing thing. No, no. There's this great question, right? Let's look at. Here's a way to think of it. Okay, in this picture here. So here's our pie chart. That's for today. In 100 billion years, the universe is still. You still have the pie chart. In 100 billion years, the slices for cold dark matter and for atoms become tiny. The whole energy density of the universe is all dark energy. And that's what keeps driving it.
We don't know what is dark energy.
And we don't know what that is. Right. We just, you gotta work on it. Okay. Yeah, no, we don't know what that is, but that's the picture. No, it's a great question.
You.
Yeah.
Question.
Professor, what made the matter actually tip and fall into the valleys in that abbreviated version of the standard model of cosmology?
Sorry, what made it fall in?
What made the matter form into the valleys?
Oh, into the valleys? Imagine, imagine you're in, what's a good example? If you can think of a valley like a bowl, right? And the matter is like a sticky bowl, if you will. The matter is a marble. And it just rolls down. And there's just some friction so it doesn't roll out the other side, right? But it rolls down. So it falls, it collects in the valleys. Another way you can imagine it, think of it as like fog in a landscape going down into the valleys.
No, what made it fall in the first place?
What made it? Just gravity.
Like when it's at the top of a crest, it would be in equilibrium, right?
No, so imagine, a way, let's see, to think about it so imagine you had a string of galaxies, or a string of marbles, and they were all equally spaced. Okay? And now just move one of them, tiny, tiny bit. Okay? If they're all equally spaced, it's an equilibrium, right? But now just move one of them a tiny, tiny bit. Now it's closer to the one next to it, right? And so now, since gravity is proportional to the inverse distance squared, it feels a stronger pull towards that one than towards the other one. So they start falling together. Okay? And then, so now those two are together, and they pull a little bit over here. But now there are other fluctuations, along this long line of marbles over here. Someone started over here, and those guys are now coming together over here, right? So if they're uniform, it's unstable to gravity, and it just takes a tiny little perturbation for them to collapse and start glomming together. That help or?
Yeah.
Yeah.
Okay.
No, that's the thing. This just gravity, just because it just pulls everything together. Yeah. But why it rolls down?
Yeah, I think you showed a picture with the valley and thing. She's asking.
But that is the rolling. That is the coming together. Is rolling down, if you will. If you think of, because it's just a way of showing that coming together is like rolling down in the valleys. With tiny quantum fluctuations.
What caused the fluctuations?
What caused the fluctuations? These are, I mean, the idea is that they came out of this process called inflation. And that there were, because in every field you have fundamental you have quantum fluctuations. There's no such, you can't have a field without fluctuations. Tiny, 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 tiny fluctuations. And that's all it took to get this whole picture going.
Okay, thank you.
Okay, is that?
This lecture is being live streamed, and so there are some questions from the virtual world. So one is, what can we expect when the James Webb Telescope is launched in the future?
Okay, so in this, let me go back to an earlier picture. Okay, so this is the picture from the, if you can, whoever's out there, hi. The picture from the Hubble Space Telescope, and it's looking back here. James Webb will be able to look back even further, and really it can do many, many things. But that's one of, in the cosmological context, that's one, is to really help us develop this picture of how structure formed after the microwave background decoupled.
So that was by Uttam Krishna. There's one by Surya Prasant. What happens when we place a gravitational wave observatory in space? I suppose perhaps what can we learn from a gravitational wave observatory in space?
You go to space. Well, there are a bunch of reasons to go to space. Absolutely after you do LIGO India. But there are a bunch of reasons to go to space, and one of them is you can look, instead of for 100 hertz gravitational waves, you can look for much lower frequencies. And with one of these proposed satellites, say LISA, you can catch those black holes a month before they collide. So you can actually go up and you can see this thing right now with LIGO. You only see the very end of it, right? The last few tenths of seconds. But you can see these things coming together for a month and study them and their spin, and it's happening all over the universe, all the time, right? And you'll just be able to see them and study them. No, it's be another fantastic mission.
Thanks for that beautiful lecture, sir. When the universe started, we had this primordial soup full of quark, gluon, plasma, and all that, right? So could this cosmic microwave background be the same primordial soup, which is not condensed yet? What's the possibility? Or is the universe infinite and it's still cooled off?
The radiation,
yeah.
This radiation is that same radiation that was interacting with the quark, gluon, plasma.
Yeah.
It's just later. Okay. So it's cooled. And I sort of picked up the story after the quark, gluon, plasma had become protons and neutrons. And so you're just talking about an earlier epoch. And so that happened, and after about 3 minutes, all the nuclei were formed, the hydrogen and the helium and the lithium and beryllium, and that happened after 3 minutes, and then I was sort of picking it up after 300,000 years. Okay, same picture, absolutely all works together. I should say one of the mind-blowing things about this, and I should have emphasized this more, right, is this picture we gave. As I had my microwave background-centric hat on when I was telling you, but if you look at just the elemental abundances, so you look at the ratio of hydrogen to helium, not using the microwave background, just looking up at the sky, and you say, is that consistent with what you see with the microwave background? And the answer is yes, to really good accuracy. I think lithium is a little bit off, and that's under investigation. And if you instead don't look at the microwave background and you look at supernova or you look at galaxies, and again, forget about the microwave background. Of course, the expansion was discovered just from galaxies. If you do everything from that point of view, you get the same picture. It's just fantastically well constrained. It's wonderful. And let me just quickly add, it doesn't mean to say it's all solved. Not everything doesn't fit together perfectly. There's still what my friend Dick Bond calls tensions, right? There's still some things that don't quite fit, and they're really interesting because they don't quite fit. It could be a measurement problem. Could be a new, a hint for something new in the model. Right now, there's disagreement on the expansion rate, for example, at the few percent level. Those are all things we love to look at because it might be a hint for something that takes us beyond those 6 parameters.
So an excellent lecture. Sir, I want to ask you, like the edge of the observable universe is basically constrained because of the light speed, right?
Yeah.
So that is why we say that 13.8 billion years is the age of the universe. Now, assuming that we have something which is faster than light, so is it possible that the Big Bang, the origin is shifted much earlier? Like, let's say 15 or 16 billion years ago.
Okay, so I missed what you said just before, faster than light?
No, I mean, assuming theoretically, if something is more faster than light,
which
is,
if
of
there
course,
is
not possible in the normal physics, but because, as you said, the universe is infinite.
Yeah. If there were causal processes faster than light, I don't know what they'd do to this picture. They'd have much more profound consequences nearby, right? I think, I'm not sure. But but your question brings up something. So how do we think about that surface? So what is the Big Bang, right? What's going on? What's this picture, right? The Big Bang happened right here, right? It happened on our, if you had a clock that was, could go back, a watch that could go back 13.8 billion years, it happened here. All these processes, it didn't happen out there. It all happened right here, right? The atoms were formed right here. The CMB light was right here. Of course, the stuff that the microwave background that was here is now long gone, but it's out at the edge of the observable universe. Structure was formed right here. We were in a gravitational potential well right here. It all happened right here, right? And that's the case for everyone in the universe no matter where they are. It all happened the same way where they are. And if you were, for example, if you could be instantly transported to the edge of the observable universe and you looked out, what, you can imagine what you'd see, right? You'd see that same picture, that same sphere, but our proto-universe would be at the edge. Our proto-solar system would be at the edge. Right? Everyone sees that same picture, no matter where they are.
You showed the bar chart with the dark energy and dark matter. And you were suggesting as we move 100 billion years ahead in time, the dark energy would win the race and it will be like 90%, assumingly.
Yeah, I just picked an arbitrary long time. Go further away, it becomes greater and greater fraction.
Was there a time when they both were in equilibrium, the dark matter and dark energy?
Yeah, so as you go back, the dark energy becomes negligible, absolutely negligible. And what happens is, as you go back, so this is another frontier, you get the matter, these guys are not, those guys are going to scale together, okay? So it's not going to be one grows with respect to the other one, because they're matter. They're all just matter. Even though we don't know what one of them is, if you put on a scale and you weigh it, it's just matter. So you could come up with something exotic, but mostly it's just matter. So those guys scale together, that 5-to-1 scales together. But that one goes down, and the other thing that happens as you go back is radiation starts to become a greater and greater part of the universe. And neutrinos, right, these particles you didn't talk about, are a greater and greater fraction of the universe. So one of the things we're doing to the microwave background now is we can make measurements precise enough, we can look back when neutrinos were a greater fraction of the universe and see their effects. We're starting to probe them. Yeah.
Hello, sir. So you were talking about the CMB radiation which were measured from satellites. Now you explained about some of the observatories which are coming up which are on ground. So what new science they can provide?
So I missed the last part, sorry.
What new science will they be providing?
What new science?
Yeah.
So, on the ground, satellites versus ground. So I should say, so these are currently going on the ground. And the thing that you get from space that you can't get anywhere else is the whole full sky coverage. And it's also a very clean environment from which to make measurements. So they're very clean measurements. On the ground, what you can get is you can focus in on a fraction of the sky and go deeper. And so there's been this complementarity for for the age of the field of going to space and ground. First there was a Russian satellite, and then there was the Kobe satellite, and then there was WMAP, and there was Planck, and there was there are a few satellite proposals around. Probably the one with the best funding is the Japanese satellite, the Lightbird satellite, and it will try to go to space to measure again the largest angular scales.
So maybe one last question.
Hi, sir. You talked about how the gravitational wave through a rod stretches it and expands it, blah, blah, blah. And same with the CMB sphere model, right? The gravitational wave can make it by a very tiny stretches it. So what if the dark energy might also be causing the same thing? How do you distinguish between what is actually causing that stretch or contraction?
Okay, so so I think the question is, how can we distinguish, say, a gravitational wave signal from the dark energy doing something funny? So the neat thing about these gravitational wave signals is they have a characteristic signature in the polarization. And there may be, there are a lot of, in the audience, there are a lot of very clever theorists, and they might be able to dream up something. But for your generic dark energy, you're not going to be able to mimic that signal. And I can tell you what it is, and that is if you can imagine, you have a picture of polarization, right? You could just imagine it as light. What does it mean? If you're polarized that way, it means light is oscillating in that direction. And if you look around the sky, it means it's oscillating in that direction or that direction or that direction. So you can think of those as as, you know, toothpicks or something, right, that measure it. And so you can just imagine, so it's random on the sky. You just imagine if you threw a bunch of toothpicks on the floor and looked at them, and then you looked at them in a mirror, and you looked on the floor and looked at them in a mirror, you'd see the patterns wouldn't be quite the same. And the ones that stay the same looking in the mirror are for the most part, not gravitational waves, and the ones that flip are. So that's the measurement we try to do, is we look at the pattern and look for the component that flips if you look in a mirror.
Okay. Before we conclude, if I can ask a sort of a somewhat personal question. You were urging the younger people to go in to projects like LIGO India. Yeah. So as an experimentalist who has spent a large part seeing this evolution of cosmology, what is it that you feel was sort of the most fulfilling the fulfilling part of this journey? Was it the designing the experiments, building them, seeing the results?
All the above. No, for me, it's just been a blast. But it's mostly, it's all great. You know, if you do experimental physics, this is the old terms. I mean, experimental physics, the lows are incredibly low because you build something and it breaks, and you build something and it breaks, and you fix it and it breaks, and then it doesn't do what you thought it would do, right? And it's just incredibly frustrating, and you go through long periods of like that. But then you build something and it measures something new, and you have seen something new in nature, and it is just, you know, a fantastic feeling. And I can tell you, my thesis was on a balloon, and it fell out of the sky and just like completely burst. I had to rebuild it and fly it again. But it's just when you measure something new, there's just nothing like it. And so there's lots of new things to be measured in the microwave background, and there's lots of new things to be measured in gravitational waves. So they're just, you know, so get involved and go for it.
So with those very inspiring words, I hope a lot of you will go in for some of the grand challenges of the future. Let me thank Lyman again.
Thank you. Thank you all. It's been great. Good.